So we've been through three of the models. We left off with Rutherford's model. Rutherford's model is really the one that introduced the nucleus because most of the alpha particles went straight through the atom, meaning it was mostly empty space. Occasionally, one of the alpha particles would come flying towards an atom and get near the nucleus, and the nucleus is positive, the alpha particle is positive, and it would repel it or scatter it off to the side. The only way that would happen, the only way a positive alpha particle could get pushed away and scattered a different direction rather than passing straight through is if there was a highly positive area in the atom, and that's what Rutherford concluded. And he also concluded that that highly positive area had to have the majority of the mass of the atom, because the only way an alpha particle, which was 2 protons and 2 neutrons, a mass number of 4, could ricochet straight back at somebody, straight back at where it came from, was if there was all the mass of the atom concentrated in a small center. Now, there was some problems with Rutherford's model. He did have the electrons orbiting the nucleus. The negative couldn't be in the nucleus, so the nucleus would be neutral. But the problem was if the electrons were negative and the nucleus was positive, why wouldn't they be repelled straight in? Because opposite charges attract. And the other thing Rutherford's model was missing was the mass of the atom. And that's going to be a problem that plagues the next two models that followed Rutherford's model, because the particle they hadn't discovered yet was the neutron. The neutron's a neutral particle, not easy to discover or prove that a neutral particle is in the nucleus. So, what ended up fixing the problem of these electrons not being pulled into the nucleus? And that's where the fourth model comes out. And the fourth model, Bohr's model, came out just a few short years after Rutherford's model. Rutherford's model was 1911. The next model came out about or around 1913. Bohr's model of the atom. Now, Bohr's model is often called Bohr's model of the hydrogen atom because, as we're about to find out, it really only explained the hydrogen atom. Yet it did make a landmark idea that changed the notion of how electrons behaved in an atom forever. And Bohr's model ushered in what was called the quantum age of science. Now, since Bohr's model and Rutherford's model came out at about the same time, just 2 years apart, they're often lumped together in what's called the Rutherford-Bohr planetary model. The planetary model has the nucleus, which is like the sun. And then from Bohr's contribution to the planetary model, the planets were like the electrons, and the electrons had to have specific orbits, the same way planets have specific orbits. So Rutherford-Bohr model sometimes nicknamed the planetary model. If we're talking about Rutherford's model by itself, we usually call it the nuclear model. Rutherford did have electrons orbiting sort of like planets, but they were not fixed, or they were not orbits that had to be in any particular place. With Bohr's model, we're going to come to find out that the electrons had restrictions on where they were permitted to orbit. Bohr's model came from an area of studying, really it came from the study of light. At this time, in the early part of the 20th century, scientists were studying what happened when atoms were energized. And they found out that if you give atoms energy, atoms in the gas state, if you blast them with electrical energy or even heat energy, you can make those atoms glow. And they began to study that glowing light that came off the atoms that were energized. And it doesn't have to be just visible light, because the energy being given off is called electromagnetic radiation. Now, radiation here is not implying nuclear radiation. The energy had nothing to do with nuclei falling apart in radioactivity. Radiate here just means given off. Electromagnetic radiation is just forms of energy that travel in waves. Light is one type of energy that travels in waves. So, When these atoms were excited with energy, they began to glow the same way that light in a light bulb glows when electrical energy goes through it. And they began to study what was in the light, or the better said, the electromagnetic radiation coming off the atoms. They began to study it. What did they do? They put that light. So here's essentially a light bulb. It's a gas discharge tube that was energized with electricity. This one's filled with hydrogen gas. So they put electrical energy in the hydrogen gas, and the hydrogen gas begins glowing. And they allow that glow to pass through tiny slits, and they directed it through a prism so that they could separate that light into bands. And they found out something quite unusual. They found out that different atoms had different spectrums that were produced when the atoms were excited. So they were studying what we call the emission spectrum. Emission means give off. Spectrum means the components of something that's making it up. In other words, they were looking at what was making up the light that was being given off by atoms that were excited. Bohr focused in on hydrogen, and he noticed something very interesting about hydrogen spectrum, that only certain bands of light were being given off. It wasn't a continuous spectrum. A continuous spectrum's a rainbow. And he made a startling conclusion about this. Hydrogen, when it was excited, did not give off a continuous spectrum. Instead, it gave off what's called a bright line spectrum. Only certain bands appeared: a red, a green, a blue, and a violet. Instead of a continuous spectrum where you saw all those. That's called a line emission spectrum, where instead of seeing all the colors, you only see certain bands. And what Bohr saw led him to make a very, very dramatic conclusion about the atom. Bohr reasoned that it was the electrons in the atom that were responsible for the spectrum being given off. And what Bohr realized is that the electrons could not have just any energy, as Rutherford thought. Rutherford said that these electrons could have any orbit, therefore they could have any energy. Bohr saw something different. If Rutherford was right, electrons could have any energy, any orbit, you would see this continuous spectrum. But for the fact that you saw only certain bands, it meant the electrons could only have certain energies. What Bohr realized is that the electrons had to be traveling in certain orbits. And many of you have seen Bohr's model. And what Bohr realized is these light bands were given off as these electrons in the atom. As the atom was energized with electrical energy or heat energy, these electrons would jump to higher orbits. And then they would return. And when the electrons return from outer orbits into where they started from, that's called the ground state, they released energy. They would release any energy if they could have any orbit. But since they released only certain bands of energy, that meant they could only have certain allowable orbits. Very often these orbits are called energy level 1, 2, 3, 4, 5, 6, 7. The spectroscopists, the scientists that study these emission spectrums, gave them letters: KLMNO, PQ. So the first level was given the letter K. The second level was given L, and they just proceeded outward. The third was given an KLM, third for the M. Fourth was N. Fifth was O. Sixth was P. And the seventh was given the letter Q. That's what the spectroscopists lettered them. Chemists tend to go with energy level 1, 2, 3, 4, 5, 6, 7. Sometimes abbreviated E1, E2, E3, E4, E5, E6, E7. Here you see the E's being used: E1, E2, E3, E4. Once again, what Bohr reasoned was, if there's an electron that was flying around on the atom, when you give it energy, if you give it the right amount, you can get it to jump to the next highest orbit. That's said to be excited. When the electrons are jumping to outer levels, the electron's said to be excited. So to get the electron to jump outward, you had to excite it. It had to take in energy. When the electron returned to where it started from, it would release energy. Since it only released certain bands of energy, it was only allowed certain orbits, and we now have the Bohr's model of the atom. What was Bohr's big improvement? Instead of having any orbit, they were only allowed certain orbits, and they were allowed to stay in those orbits. The electrons wouldn't get pulled in because they had to have a certain amount of energy to stay in that orbit. Now, the problem with Bohr's model, it really only worked for hydrogen. Only these bands would explain the energy levels associated with hydrogen's electron. When you got to larger atoms, the bands didn't quite line up with the energies that were associated with those levels. And it also didn't explain the intensities of certain lines or the appearance of certain lines. So Bohr's model was a great advancement, but there must be more to the electron than traveling in certain orbits. There had to be more to the electron. And in our next video, we will put in the things that will solve the problem with Bohr's two-dimensional flat orbits. And that will take us to Model 5, which we call Schrodinger's quantum mechanical model, also called the electron cloud model. It came out about a decade or so after Bohr's model. And we'll save that for the next video.